Hello everyone, welcome back to my channel Dr. As. In today's lecture, we'll discuss about concept learning and general to specific ordering. As far as the topics that are concerned, we'll be talking about the introduction part of concept learning. Then we'll discuss about a concept learning task. And finally, we'll talk about concept learning as a search. Now, coming to the introduction part, we generally think of concept learning as a searching problem where we search for an appropriate hypothesis that best fits the training example, and these hypotheses that we are searching from come from a predefined space of potential hypotheses. Any activity of learning generally involves acquiring general concepts from given specific training example, and that is what we consider as concept learning. Generally, concepts can are thought about as Boolean valued functions. For example, a function that is defined over all animals can be true if the animal is identified as a bird and false if the animal is not identified as a bird. So finally, concept learning is all about inferring Boolean valued functions from the training examples of its input and output. So with this, we come to the end of our introduction part. Now we move on to understanding a concept learning task. Within this, we discuss about two topics. One is description of concept learning task, and we'll also discuss about the notations that are given for a concept learning task. Now, moving on to description of a concept learning task, let us consider an example. Here, what we are trying to learn is we are trying to learn the concept the days on which I enjoy my favorite water sport. So this is what we are trying to learn here. The given table describes a few examples. In this table, we have 6 attributes which describe the conditions on a given day. And we have one last attribute which is called as enjoy sport, and this is the one which is going to tell us whether I enjoy. If I enjoy, it is going to be yes. If I do not enjoy, it is going to be no. What we are trying to do here is we are trying to hypothesize this target concept. So in order to hypothesize this target concept, we need to have a representation for the hypothesis. Here, let us take a very simple representation of the hypothesis, which is going to be a conjugate hypothesis, and it is nothing but a conjugate of the given 6 instance attributes. Now in this hypothesis, each attribute, for example sky or air temperature, each attribute can have different possible values. The attribute can have a question mark which indicates any value is acceptable for this attribute. For example, if you look at this example, it can accept sunny or rainy. In fact, one more value is there for this attribute, which is also cloudy. It can accept sunny or rainy or cloudy. And the hypothesis attribute can be represented by a phi, which indicates no value is accepted. Or the hypothesis attribute can be represented by a specific single required value like sunny or rainy. So for example, this is a hypothesis where the first attribute is rainy, which is a specific value. Second is a question mark, which says second is a question mark for this question mark is for the second attribute air temperature. So and this is telling us that the air temperature can be warm or cold and so forth. And this is also a hypothesis where we have all the question marks, which means that all the attributes can have any values. And finally, this is also a hypothesis which is all 5, which says no value is accepted for any attribute. Now moving on, any concept learning task can be described by these 4 components. The first one is the set of instances over which the target function is defined, represented by capital X. The second one is the target function, which is represented by small c. Then the set of candidate hypothesis considered by the learner, which is represented by capital H. And finally, the available training examples, which is represented by capital D. Now let us come to the notation of the concept learning task. The notation has all the 4 components, namely instances, hypothesis, target concept, and the training examples. When you look at the instances, there are 6 different attributes in the instances, and the sky attribute, as we can see, has 3 values, namely cloud, sunny, cloudy, and rainy. Air temperature has 2 values, warm and cold. Humidity has normal and high. Wind has strong and weak. Water has warm and cool. And forecast has same and change. These are the instances. Now looking at the hypothesis space or hypothesis. The hypothesis in addition to the instance space has 2 different values. One is the question mark and the other one is the phi. So other than that, all the 6 attributes have the values, namely sunny, cloudy, and all. That is what is the hypothesis that we have. Now moving on to the target concept. The target concept is a function named enjoy sport, which maps from the instance space to a Boolean function, Boolean value 0, 1, where 1 can be yes and 0 can be no. Finally, the training examples D, which are positive and negative examples of the target function. So what we are going to do in concept learning is we are going to determine, or we are trying to find a hypothesis H which belongs to the hypothesis H, capital H, such that H of X is equal to C of X for all X in capital X. So that is what is about the notation of concept learning as a task. So with this we come to the end of concept learning task. Now we move on to the next one, which is concept learning as search. Here we discuss about 2 things. Number 1 is concept learning as search, and number 2 is general to specific ordering of the hypothesis. So we now start with the concept learning as a search. So we look at concept learning as a search. So what are we searching and where are we searching? That is what is very important. So coming to the second question, where are we searching? We are actually searching through a large space of hypothesis. And this hypothesis is defined by the hypothesis representation, which we have discussed earlier. The hypothesis representation for our task is a conjugate hypothesis of all the 6 attributes. So now what is the goal of this hypothesis search as far as the concept learning is concerned? We are searching actually for a hypothesis, one or a few hypotheses that best fits the training examples. That is what is the hypothesis that we are searching for. Now, what is the size of the hypothesis? What is the space of the hypothesis? It all depends on the hypothesis representation. As we have discussed earlier, we have taken a very simple hypothesis representation, which is a conjugate hypothesis space. So now let us see what is going to be the size. What is going to be the size of the instance space and the hypothesis space. Now coming to the instance space, Let us try to understand what is instance space. Instance space is a space from where all the instances are being drawn. So now coming to the size of the instance space, the first attribute, which is sky, has 3 values. Second attribute, which is air temperature, has 2 values. The third one, which is humidity, has 2 values. The fourth one has 2 values. Fifth one has 2 values, and sixth one has 2 values. Therefore, the size of the instance space is 3 into 2 into 2 into 2 into 2 into 2, which is equal to 96, which means that there is a possibility of having 96 distinct instances. And moving on, let us try to understand the hypothesis space. Now in the hypothesis space, in addition to the 3 values, for example, let us take this sky attribute. In addition to the 3 values that are there in the instance, there are 2 more values, which are the question mark is question mark is 1. Let me put it properly. And the second one is 5. So 3 plus 2 makes it 5. Similarly, for all the other attributes also, 2 plus 2 makes it 4. Similarly, for other attributes, 4, 4, 4 and 4. So therefore, 5 into 4 into 4 into 4 into 4 into 4 is equal to 5120 distinct hypotheses that we have here. And all these 5120 hypotheses are syntactically distinct hypotheses. Now, among the 5120 hypotheses, if you look at a few hypotheses, they contain one or more phi value. And all these hypotheses represent empty set of instances, and they classify these instances as negative. Therefore, we remove all those hypotheses and retain only one representative from all those hypotheses containing phi value, and which is all phi hypotheses. And now the remaining hypotheses are going to be 4 into 3 into 3 into 3 into 3 into 3, as we have lost one value, which is phi, in all the hypotheses. So therefore, semantically, we have a total of 973 hypotheses. Now, as we are looking at concept learning or learning as a search problem, what we are trying to do is we are looking for different strategies for searching the hypothesis space, because we are looking at the problem as a search problem, and where we are going to search is nothing but the hypothesis space. Therefore, we are looking for different strategies for searching the hypothesis space. Generally, any learning algorithm will be interested in algorithms which can efficiently search through infinite space. But here, as we have a very small problem, we will be finding algorithms where we can search through 973 distinct hypotheses. So now we have to look at the strategies that we are going to use for searching through the hypothesis. The concept learning problem has a naturally occurring structure which is called as the general to specific ordering of the hypothesis. This particular structure, which is the general to specific ordering of the hypothesis, can help us in designing learning algorithms that can completely search or exhaustively search hypotheses which are big, not only big, which are infinite in space, without explicitly enumerating each hypothesis. What do I mean by explicitly enumerating each hypothesis? I need not go to each and every hypothesis and search, but still I'll be searching the entire space exhaustively. To better understand the general to specific ordering, let us consider an example here. We have two hypotheses, H1 and H2. H1 is sunny, question mark, strong, question mark, whereas H2 is sunny, question mark, question mark, question mark, question mark, and question mark. If you look at both of them very closely, H2 imposes fewer constraints on the instances and therefore classifies more instances as positive in comparison to H1. So what we can say is, we can say that H2 is more general than H1. Now we need to give a proper definition for this more general than. To understand the more general than relationship, we need to understand a few prerequisites. First, we need to understand what we mean by satisfies. For any instance small x in capital X and hypothesis small h in capital H, we say x satisfies h if and only if h of x is equal to 1. What do we mean by h of x is equal to 1 is the instance x properly fits into the hypothesis h, or the instance x is part of the space that is covered by the hypothesis. Now the second prerequisite that we need to talk about is understanding more general than or equal to. Let us assume we have two hypotheses, Hj and Hk. Both these hypotheses are Boolean valued functions and these are defined over the instance space X. Now we say Hj is more general than or equal to Hk and we write it as Hj is more general than or equal to Hk if and only if for all the instances small x belonging to the capital X, if Hk of x is equal to 1 implies Hj of x is also equal to 1. It means that an instance x, if it satisfies Hk, then it also satisfies Hj. Then we say that Hj is more general than or equal to, more general than or equal to Hk. With these two prerequisite relations that we have defined, now we can define the more general than relationship. We say that Hj is more general than Hk, which is written as Hj more general than Hk. Here if you observe, we don't have this equal to, here. If and only if Hj is more general than or equal to Hk, but Hk is not more general than or equal to Hj. If Hj is more general than Hk, then we can say that Hk is more specific than Hj and Hj is more general than Hk. Let us look at an example to understand the general to specific ordering better. Here we have two spaces, one is the instance space and the second one is the hypothesis space. In this hypothesis space, we see all the hypotheses from general to specific ordering. There are three hypotheses, namely H1, H2 and H3 in this hypothesis space. The question that we need to answer here is which hypothesis is more general than the other hypothesis. To answer this question, let us look at an example. We have two instances x1 and x2 and three hypotheses h1, h2 and h3. The instance x1 satisfies h1 because we can see the sunny can be kept in the first place where it is sunny. So warm can be kept in the second place, which is a question mark. High can be kept in the third one, which is a question mark. Strong can be kept in the strong. The strong instance value can be kept in the strong value, and the other two, cool and same, can be kept in the question mark. So therefore x1 satisfies h1, but x2 does not satisfy h1 because the fourth attribute in x2 is value is light, whereas in h1 the fourth attribute value is strong. Therefore x2 does not satisfy h1. So if you see the space or the instance space that is covered by h1, we have x1 is part of this space, but x2 is not. X2 is beyond the space that is covered by h1. If you look at the second hypothesis, which is h2, we can clearly see that both the instances x1 and x2 satisfy h2. So therefore the instance space that is covered by H2 is a huge space where both x1 and x2 are part of it. If you see H3, x1 is covered, so x1 is part of the space, but x2 is not part of the space. So because H2 has two instances, x1 and x2, satisfying it, we can clearly observe that H2 is more general than H1 and H3. So therefore, H2 is towards the general end and H1 and H3 are towards the specific end. But we cannot clearly say among H1 and H3 which is more general and more specific. So therefore, both of them are at the same level. So this is an example which helps us in understanding the general to specific ordering better, or the more general than relationship better. With this, we come to the end of this lecture. So thank you for patiently watching my lecture. Please do like and subscribe my channel, Bakras. Thank you very much.